Do parallel universes even exist? Or are they just some myth that is told by people who write sci-fi movies and books? Well, according to quantum mechanics, maybe they do. But before you try to go meet your parallel selves, there is a catch. In order to understand this, we need to understand some quantum mechanics. So let's get to it. Let's set up an experiment to investigate the quantum world. Here we have a source, and we also have two walls. One of the walls has two slits in it. Let's see what happens when we shoot some balls at it. Well, obviously, since the balls are particles, some of them go through the holes, and some of them get stopped by the wall. What happens if we shoot light instead, which is a wave? What we get is an interference pattern. And we get this pattern because of the wave properties of light. And because of the wave properties of light goes through both of the holes at the same time, as shown by here. And at some points where it goes through the holes, there are points where the two waves intersect. And these points of intersection are very important. It's called interference points. And that's where two waves meet. And when two waves meet, they can either build up each other. This is called instructive interference. Or they could cancel each other out. This is called destructive interference. Now, interference is a very important topic in quantum physics, so remember it. So this is cool and all with light. But what happens if we do electrons instead? Well, you would assume, since electrons are particles, that something like this would happen. But what we actually get is an interference pattern, just like light. Now, why would we get an interference pattern? Now, why would we get this interference pattern? Isn't electrons like particles? Well, it turns out that particles can exhibit wave-like properties. And it also turns out that waves, like light, can have particle-like properties. How is this so? This is known as a wave-particle duality. And it basically says there's some relationship between waves and particles. But how are they connected? How can waves act like particles and particles act like waves? There must be some kind of connection in between them, and this connection is given in the wave function. But what is a wave function? Well, simply put, a wave function is a probability graph. It gives the given probability for every output. But what does this mean? So I have a pair of dice here, and when I pick up the dice and I roll them, I get some random value. For here I got a 3 and a 2, so I got 5. But when I'm rolling them in my hand right now, as you can see, they really don't have any value until I roll them. 6. The same goes with particles in quantum physics. So imagine that each dice is a particle here. And as I roll the dice, before I measure a particle, they are in this state. We don't know what state they're in. We don't know their properties. But when I measure the particle or roll the dice, I get some state and properties out. Now, what are these states and properties? How do you predict them beforehand? Well, as with dice, they're pretty much random. So the only way to predict them would be through a probability graph. So the probability of the dice would be given by probability graph. And let me just draw one real quick here. So this is a very rudimentary graph. It's not really accurate, but it should serve our purposes. As you can see here, 6 has the highest probability of being picked. Probabilities for 2 and 12, though, are very small. Before we roll the dice, it doesn't have one specific output. Its values are actually just a probability graph because we don't know what is it going to be. But after we roll it, it gets one specific output, 9. So before we roll it, before we measure it, this is this value, literally this graph. But after we measure it or roll it, it gets something like this. A single particle at the value that we rolled it at. In this case, it's 9. Now, this is known as the wave function. So the wave function is the probability of where the a particle will appear. So if this was a wave function of a particle, there'd be more chance that it would appear over here than, say, over here. But after you measure it, though, it could appear anywhere. But we know the probabilities. We can't get the exact value of where the particle would be, but we can find the probabilities of where it would be. Now, once we measure it or look at it, the wave function collapses to a single particle. Why does this collapse? That's still a big mystery. So basically, to summarize what you've learned so far, scientists, by doing different experiments, have figured out that particles can have wave-like properties and waves can have particle-like properties. This is known as the wave-particle duality, and it hints that there's some greater connection between particles and waves. This connection is given in the wave function, and the wave function is just a probability graph, and when you measure it, it collapses into a single particle with definite values. Whoa, that's a lot of information there. So if you need to rewind and watch the video, please do so, as the next part is going to build on that. So you might have a lot of questions from the last part. For example, why does a wave function turn from a wave into a particle? Why does it collapse? And the question of why it collapses has actually been a problem for many physicists for a long time. And still, nobody has a good answer for it. This is where many worlds come in. So to start to understand it, let's say that there's you and a particle. Okay, so the particle could be either in a state of positive charge or a negative charge. But before you measure it, of course, it's still in the wave function. And it could be either a positive or a negative. And we call this superposition. That it could be, it's positive and negative at the same time. It could be either positive or negative when you measure it. Alright, so it's superposition of positive and negative. And also, you are also a wave function. Just so you know, you're also made up of particles. So you have your own wave function too. So this right here will be the wave function of you. This is a particle. Okay, let's see what happens. So when two wave functions interact with each other like this, they get entangled together, or they become one wave function. This is the wave function of you and the particle. Now let's go back real quick and see something. The particle is in a superposition of a plus and a minus, alright? So particle is in a superposition. But once you and the particle become one wave function, because that's what happens when two wave functions interact with each other, they become entangled together. So once they become the same wave function, you become part of that superposition. Now what does this mean? That means you're in superposition of measuring a positive when you measure the particle, and you measuring a negative when you measure the particle. There's two U's and they both measure different values. You're in superposition of those two states. So in order to solve this, of course, physicists have come up with like the whole wave function collapsing. So then if the wave function collapses, see if the wave function, once they interact here, the particle wave function collapses to a single particle, right? Then there's no entanglement, and then you don't become part of the superposition, and you just get a single value. But if you ignore that, this is what happens. And this messed superposition doesn't even make sense. How can you measure a positive and negative at the same time? When we measure a particle, we either measure a positive or a negative. We can't measure both. But what if a world where you measure positive is different than the world where you measure negative? What if for every outcome, there's a separate world, the world split? So before there was just you and your particles world, right? But now there's two worlds, one where you measure positive and one where you measure negative. This is many worlds theory. But what does this mean? Well, basically, anytime anything happens, anytime you make a decision, anytime scientists make a measurement on a particle, our world branches off into two different worlds, and each outcome of this measurement is represented in a different world. To summarize everything that we learned so far, in quantum mechanics, there's something called the wave-particle duality, which shows that some particles could act like waves and some waves could act like particles. This connection between waves and particles is given in the wave function, which basically says that before measurement, a particle lives as a wave function, which is a probability graph of where it's going to appear. But once you measure it, it has a definite particle with definite states and properties. Now, in order to explain this change from a wave to a particle, scientists have come up with the many worlds theory, which basically says that every time you make a measurement, two different worlds branch off, and every probability is represented by one world. There are many problems with this theory, which I will not be going to in today's video. If you would like to see a video dedicated to this topic, please post it in the comments below. If you have made it this far through the video, please go to the description and fill out the little survey I made, which will help make my videos more catered to what you want. Well, that's it for today's video. I guess if you want to, you can like and subscribe down below, please. Alright, see you next time, and thank you for watching.